If you have spent some time exploring the world of physics, you may have come across a strange concept known as the wave-particle duality of light. Essentially, it has been observed that light, which is made of particles called photons, does not behave only as a corpuscle, that is, as a particle, but also shows wave-like behavior. Both descriptions of light coexist, and they represent the same phenomenon, seen in two different ways. But what if I told you that we, too, besides being made of particles, also have a wave-like nature, and that, in general, all objects with mass exhibit wave-particle duality? Today, we will explore the experiment that revealed this, leading us to an equation valid for all bodies which describes their wavelength. At the beginning of the 19th century, the physicist Thomas Young performed for the first time an experiment known as the double-slit experiment. Young was working in optics, the branch of physics that studies light and its behavior. He wanted to show that light from a source after passing through two slits and then reaching a screen would produce an effect caused precisely by its wave nature. This effect is called interference. In physics, waves are usually represented as oscillating functions. They have an amplitude, which measures the maximum displacement of the oscillation, a wavelength, which is the distance between two consecutive peaks, and a frequency, which tells us how many oscillations occur in a given interval of time. In this representation, when light comes from a source, it propagates in all directions. And when it reaches the two slits, those slits behave like two new sources of waves. Young was interested in understanding how these two waves would interact with each other. The effect he was trying to produce, and that he actually managed to produce, was interference, an alternation of bright and dark regions on the screen, produced by the different ways in which the light coming from the two slits interacted. This showed that light behaved as a wave, and for a long time this idea remained the dominant description. Things began to change between the 19th and 20th centuries. Physics, which many believed was almost complete, was no longer able to correctly explain certain physical phenomena. We are talking about blackbody radiation, the photoelectric effect, and atomic spectra, phenomena that classical physics could not fully describe. The problem was not a lack of research. The problem was that these phenomena seemed to contradict the idea of light as only a wave, and instead suggested that light also had a corpuscular nature. Thanks to the work of Max Planck and Albert Einstein, physicists began to understand that light could behave as if it were made of discrete packets of energy. These packets would later be called photons. A photon is the quantum of light, and it moves in vacuum at the constant speed. C equals approximately 3 times 10 to the 8 meters per second, the same fundamental constant that also lies at the heart of Einstein's theory of relativity. But then, if light can behave like a particle, why did Young observe an interference pattern and therefore a wave? To understand this, we need to return to the double-slit experiment, but this time in a much more modern form. Let us reproduce Young's experiment. If light behaves as a wave, we expect to see interference again, exactly as happened in the original experiment. Light leaves the source, propagates through space, reaches the two slits, and then arrives on the screen. If instead light behaves as a particle, as suggested by more recent discoveries, we would expect photons to be emitted from the source, pass through one slit or the other, and then hit two different regions of the screen, following two possible paths, without producing interference. But the reality is much more subtle. Both behaviors can appear depending on whether the experiment gives us information about the path followed by the photon. If no information is available about which slit the photon passed through, the wave-like nature appears and we observe an interference pattern. If instead, a physical detector is placed near the slits in order to determine the path, the interference disappears and the result becomes particle-like. But how can physics behave in this way? The answer lies in quantum mechanics, a theory that is deeply counterintuitive because it challenges our ordinary idea of reality. Without a detector, the path followed by light is not determined in the classical sense. In quantum mechanics, this uncertainty is described through probability. We do not need to enter the full mathematical structure, but we can say that there is a certain probability of detecting the photon in one point rather than another. More precisely, as long as we cannot determine which path the photon followed, The different possible paths all contribute to the final probability. And because these possibilities are not distinguishable, they can interfere with each other. This is why the wave-like nature appears on the screen. The interference pattern tells us where the photon is more likely or less likely to be detected. Everything changes when a detector is introduced. In that case, the path information becomes physically available. The two alternatives, passing through the first slit or passing through the second slit, become distinguishable. And once the paths become distinguishable, they no longer interfere. This loss of interference caused by the physical interaction with the detector or with the environment is related to a phenomenon known as decoherence. So the two descriptions are not simply wrong alternatives. Light shows both wave-like and particle-like behavior. It is our classical intuition that finds this difficult to imagine because we are used to thinking that something must be either a wave or a particle, but not both. Let us take one more step forward. The wave-particle duality of light created a bridge between waves and particles. Around the same period, Einstein introduced the famous relation E equals mc squared, which created another bridge, the one between mass and energy. And it is here that the physicist Louis de Broglie had a brilliant idea. He asked himself if light, which we usually describe as a wave, can also behave like a particle, then maybe objects with mass, which we usually describe as particles, can also behave like waves. To understand this idea, let us consider two equations. The first one is E equals h times F. This is Planck's relation, and it describes the energy of light in terms of its frequency multiplied by a constant called Planck's constant. His second one is E equals p times c. This relation comes from relativity, and it describes the energy of light in terms of its momentum and the speed of light. Since both equations describe the energy of light, we can combine them and write hf equals pc. Now, for a wave, the speed is related to its wavelength and frequency by the relation v equals lambda times f. And for light, this speed is c. So we can write c equals lambda times f. By substituting this relation into the previous equation and simplifying, we obtain lambda equals h divided by p. This is the de Broglie wavelength. And the revolutionary idea is that this formula does not apply only to light. It applies in principle to every physical object with momentum. It connects the wavelength associated with a body to its momentum. In the non-relativistic case, when the speed is much smaller than the speed of light, the momentum can be written as p equals m times v. This formula allows us to understand why we do not notice this wave-like nature in everyday life. Planck's constant is approximately h equals 6.626 times 10 to the minus 34 joule seconds. It is an incredibly small number, and compared to the ordinary values of mass and velocity that we are used to, this means that the wavelength associated with macroscopic bodies, planets, or even larger objects does exist, but it is far too small to produce noticeable effects. On the contrary, microscopic particles can have wavelengths that are not negligible, and for this reason, their wave-like behavior becomes much more evident. So wave-particle duality is not only a property of light, it is an intrinsic feature of reality itself. And with this, we have finished. We have taken a brief journey through the quantum crisis of the 20th century and through the revolutionary ideas it produced. If you enjoyed the video, consider subscribing to the channel and leaving a like. Thanks for watching, and I will see you in the next video.